Okay, so retrodiels is simply a matter of working in reverse. Now, this is actually, I wouldn't say it's near and dear to me in terms of great memories, but this is something I actually had to do in graduate school because these cyclopentadienyl rings can actually form organometallic complexes. Okay, so if it's deprotonated, you're going to have an anion that's going to be aromatic, and it can sandwich or make complexes with other types of metals and what have you, working as what is referred to as a ligand. All right, so notice here that you have a dimer of this particular compound. Okay, so that means you have two hydrogens up here at the bridge carbon and two right here. So you have two at the top. Call them bunny ears, whatever you want to call them. All right, so if we wanted to put things in reverse in terms of a mechanism, we're just going to push our electrons over. Okay. And sorry, those arrows don't look Da Vincian in quality, but yeah, I think you get the drift. Okay, so in other words, basically working in reverse of what you've seen up to this point. So notice how things are heated and reverted back. Now, if you just had cyclopentadiene in a bottle, which is what we had because it's a liquid, eventually it would freeze up. So this is a solid. So I could put this in little s, and put this in little L italicized. Okay, so we have a solid and a liquid. So heating it up, we're going to create more entropy, breaking things up, more disorder, right? So going from 1 to 2 molecules. So just gave it away. Increase in temperature means increase in disorder, or delta S. Right? Okay, so in other words, it's applicable to reverse reactions. All right, so if so that means there's really no energetic barrier to reverse things in this particular instance, at least with heat. So let's look at problem 24.52 on page 1240, and let's work through this together. Again, really we're just going to be pushing some electrons here to reestablish some pi bonds and break up the sigma bonds. So push these back, push these over. You're going to get diene, cyclohexyldiene, and then you're going to get ethene as your dienophile. Okay, so again, just working in reverse here. Now there's not a whole lot of stereochemistry to be mindful of here. So this is a quaternary carbon, quaternary carbon. If we do everything in reverse, okay, we're going to get our dienophile, which is going to have all 4 electron withdrawing groups. Coo, cuckoo, cuckoo. Again, those are carboxylic acids. All right, and then we'll have this for our retrodiels products. All right, pretty simple and straightforward. It's just kind of like learning to drive in reverse, right? Just pushing the electrons back over. Okay. So we're now going to take a look at some potassium permanganate or oxidizing reagents to see what kind of products you can generate. Now, notice that I'm not going to cover every single minute detail with some of these. Some of the ones that I am going to cover, you're definitely going to see on the exam. But be mindful, since you're going to have the full 2 hours to go through the exam, I would kind of have this portion of your book earmarked so you can kind of pick out what the right products are going to be, because really the devil's in the details if you're using iodine or something like that, or low temperature or high temperature, etc. Okay, so potassium permanganate cold is going to be KMnO4, as you're already familiar. Okay, so this oxidizes an alkene to a cis-diol via a 4,2 cyclo addition. But at higher temperatures, it actually breaks up, let's say, a tetrasubstituted alkene to form two ketones. So in other words, it pretty much just severs this bond and has oxygen in its place. You can take a look at some of the mechanisms within the chapter. Really, right now, I'm just trying to get you guys geared up for, thinking of synthetic strategy. I know the devil's a little bit in the details with some of the mechanisms, but mechanistic questions are not really something that I'm going to be asking of you, and really not something that ACS or someone would be asking of you anyway. So, okay, so let's think of some. So this is really the strongest or furthest way you can go in terms of oxidation states, right? Unless you were to oxidize that with KMnO4, or you couldn't oxidize that any further unless you switched up and used something like what's the reagent off the top of my head? MCPBA. Sorry. Remember, that's also an oxidizing agent, so that could turn either of these into an ester. So let's think back to intermediate aldehydes. So this gets fully oxidized to carboxylic acids, or simply CO2 for vinyl or general alkenes. So in other words, if you were to react this with KMnO4, and this is going to be basic KMnO4, just remind you. So you're going to get, split that up, you're going to get acetic acid, after a proton workup or something. So KOH. And then you're also going to have, that carbon is going to get fully oxidized to form CO2. Just going to bubble out as a gas. Okay, so why don't you take a look at 24.58 on page 1241 and predict what the starting material would be. And we'll go over those examples in about 5 minutes. So pause.